So, okay, it's my pleasure to open the last session of this wonderful meeting. And our first speaker is Professor Gyan Prakash from HRI Allahabad, Prahlad, sorry, who will talk about monochromatic sums of squares. So
okay.
please.
So thank you very much. So thanks to Saurabh, Prahlad, and Balu sir for inviting me and giving this opportunity. And thanks also to my co-authors, Olivier, Malisham, and Surya, for allowing me to be part of this work. So let me, first of all, so the problem, my purpose of this talk is to not just explain the problem and give you a sketch of the proof. The entire details are a little technical, so I won't be able to do it. But to illustrate the use of two very elementary ideas which are used in this work, which I believe are something which are applicable also in other situations. So whenever you see, even if you can't follow all the talk, as I mentioned, the details are technical. Whenever I mention the work of Sarkozy and Lev, your antenna should, you should wake up if you have slept. And whenever I mention the Klein-Millman theorem, you should wake up and listen to it. Because, okay? So let me first explain the problem. So the problem was raised by Sarkozy. I forgot which year, 2001. That suppose you have the set of squares, then Sarkozy asked the following question, that for any k coloring of A, so for those who don't know the k coloring of A, anyway I will define, this is nothing but the partition of A into k many parts. Okay, so that is what you say is a coloring. That every large integer can be represented as a monochromatic sum of at most s squares, and estimate the smallest such s is equal to sk. Okay, so let me make it somewhat more precise, and also consider the analogous problem with primes. Here you are taking the set of squares, replace the set of squares by the set of primes. So this is a little more things that, so given k greater than or equal to 2, find the least s is equal to sk. So the given integer, this will be a natural number which will depend upon the k, such that no matter how you partition the set of squares into k many parts, you can, and if the n is sufficiently large, there always exists I is equal to in, and this x1, there are as many squares in this partition ai, such that n is equal to summation j is equal to 1 to s xj square. Okay, so all this xj squares belongs to the same partition, which we say is the same of the same color. So they are monochromatic. Okay, so and the analogous problem is also considered for the set of primes. So now what are the previous results? So Hegivari and Francois Henneca, they obtained the lower bound for this problem, and actually which turns out to be very close to the optimal possible, as we will see. So they prove this bound, sk is greater than or equal to k exponential log 2 plus little o of 1. So as soon as this little o of 1 comes into the picture, of o of 1 comes into the picture, you know what we are talking about is for sufficiently large k, because unless you I tell you how explicitly this little o of 1 matters, gives you nothing, no information about the small values of K. And they and for the upper bound, what they proved is this C into K log K to the power 5. C can be taken to be a 10 to the power 9. But there is a difference in the power of K itself within the lower bound and the upper bound. Okay. For the set of primes, so this SP is when this SK, I am denoting the problem for the set of squares, the corresponding bounds. And for when you take this A to be the set of the primes and consider the problem, for that number, I am denoting this SPK. So then Hagiwari and Haneke, they proved this lower bound, K into log K into this is gamma is an Euler constant. This. And SPK is, they obtained also upper bound, 1500 KQ. So, Surya and Olivier, in 2014, they obtained this SPK is less than K into log K, which in the light of this bound, because there is a lower bound also of the same order of the magnitude, K log K or K log 4K, they are the same order. Then this is optimal up to a constant. So for the set of the primes up to the constant, the problem is resolved, that you have a upper bound and the lower bound of the same order. Then in 2015, Akhilesh and Surya Ramana, they improved upon this result of Hagiwari Haneke. This K log K to the power 5 was replaced by K to the power 2 plus epsilon. Okay. So the exponent 5 here was replaced by slightly larger than 2. Then for the set of prime squares, Malesham and myself and Suri, we proved this SP square K is less than equal to K exponential 3 log 2 plus. So this, the lower bound which I have mentioned for the set of squares, is it? Yeah, here. This will work also for the prime square. So therefore, this SP square also is close to the optimal, except that here the constant of log 2 is 1, and here the constant of log 2 is 3. So bearing that apart, it is close to the maximal possible. So for the set of, in today's talk, this is a work from the 2017, so reasonably old work, which I will mention, try to give you a sketch of the proof for this SK upper bound for the K exponential 3 log 2 plus little o of 1 log K by log K. So just let us recall what is SK. So you are taking the set of squares, giving a K coloring, then you want to write down every sufficiently large natural number n as a sum of s many squares. So let us first consider the lower bound of which is due to Hagiwari and Haneke. So for this, so when I want to obtain a lower bound, what I can do is that I will define a coloring of the set of squares, means I will define a partition of the set of squares, and then give you arbitrarily large natural numbers which cannot be written as a sum of few squares, a few monochromatic squares. That will give you a lower bound for the SK. Okay. For the obtaining an upper bound, I have to prove it for the every coloring. For obtaining a lower bound, I can give you a coloring with the and then say that there are arbitrarily large natural numbers which cannot be written as a sum of few squares. So so now I define the coloring. So the coloring is defined according to the residue classes. So how do we define? We take this to be the product of first m many primes. And now, so now the squares I define, so either they are co-prime to or they are not co-prime to So if they are not co-prime to I define according to the least prime of uj, which divides them. Okay. So since is a product of the first m many primes, there will be if the set of squares is not divisible, is not co-prime to that there will be the smallest prime, which divides as well as n. So I consider that. Okay. And then the other part, I take any residue class in Z mod UMZ star square. So the R is a square of a invertible element in Z mod UMZ, and then consider n squares such that n is congruent to R mod UM. Okay. Sorry. N square is, there is a typo here, it should be n square is congruent to R mod U1. Okay. So how many colors I have chosen? So, I have chosen the number of squares plus number of divisors of number of primes, this m many primes. So the number of squares are this many in this Z mod UMZ star. So I have product Pi minus 1 by 2 and then this m. So this is my total number of colors which I have used. We have used to define this coloring. Now consider any n which is into L and L is co-prime to Okay. Then if you want to write this n as a sum of monochromatic things, first thing you notice is that none of these xi's can have a prime divisors which divides because these xi's are the squares. So if xi has and has common prime divisors, that means that they will have, because and also these are monochromatic, that means the smallest prime which divides them must be same. Which means since it is a square, now if a square is divisible by 2, then it is divisible by 4. If a square is divisible by 3, it must be divisible by 9. So therefore, all these xi's must be not only divisible by that prime, but also this prime square. So the left hand side also must be divisible by the prime square p with p dividing But this this n is by choice is taken to be into L. So if the prime is dividing the p square is not dividing it. So therefore you cannot, that will be a contradiction. That means that all these xi's must be congruent to some R mod Z mod UMZ star with R co-prime to UM. But that means also because they are monochromatic, that means that there is a common R, which such that this xi is congruent to that R mod UM star. Which means that if you read this equation modulo then what left hand side is 0 and the right hand side is R into S. Which are co-prime to which means that S must be at least because R into S is congruent to 0 mod and R is co-prime to so that means S is congruent to 0 mod which means that S must be at least because S is not 0. So when you do that, then then you use some elementary asymptotics that how the PM, the mth prime behaves and things like that. And then what you get is this lower bound. So, okay, so now let us see how we are going to attack understand this problem. So, okay, so first thing which we will, okay. So now there is a technical condition which will come to later, that what we try to do is not just take the set of all squares, but we get rid of those squares with whichever small prime divisors. Okay, so we consider, so and we will, so if this is a subset of squares, so if I have, there is a coloring of the partitioning of the entire set of squares, that means any subset of it is also is being partitioned. So partitioning of a bigger set induces a partitioning of a smaller set. Okay, so and we will try to write down our sufficiently large natural number in terms of the monochromatic sounds from this partition. Okay, and but we have to ensure that we are not losing too many things, and that is because our K is fixed, the Eratosthenes Sieve, which is in other words just a principle of inclusion and exclusion, assume that B intersection n to 4i is greater than square root n by C log K. Okay. Now, if you notice here, I can verify this, that this function in the order does not change if the K is replaced by K log K. Okay. So K log K, if I consider the right hand side function Gk and then Gk and Gk log K have the same order. Okay. So and also now the total number of squares in these intervals are square root n, and then we have only lost log K, the many, and which is all right for our purpose. And why this condition is there, we will come to see later, that we need that condition. So I'll write this Bn to be B intersection n to 4n. Okay, so now since A is set of squares, so A is that means that given any partition of A, it will induce the partitioning of this Bn as well, because Bn is a subset of A. So for sufficiently large n by the pigeonhole principle, there will exist I naught belongs to 1 to K, such that A I naught intersection Bn is Bn by K, which is greater than equal to square root n by, because Bn we have in the last one, principle of exclusion, this proved is square root n by log K. So it is square root n by C log K. So therefore this will be square root n by C log K log K. So I'll denote by A is equal to Ck log K and Sn is equal to Ai naught. Consider this one, intersection Bn. So Sn is greater than equal to square root n by A. Okay, so we shall show that the Sn with this thing S less than equal to A, this thing, which A is K log K, so this function is same as essentially the function which we are trying to bound by. So this, because as I mentioned, Gk log K and G of K are of the same order of the magnitude. So contains an interval In such that, so this S of Sn contains the interval In such that every integer in this interval can be written as a sum of elements from this Sn. Okay, yeah, so this S times Sn contains this interval, which means that this elements in this interval In can be written as a sum of monochromatic squares. Okay. And this, as you change vary n, this interval in will change, Sn will change, but nevertheless, they are all monochromatic sums because we are saying that S into Sn is a monochromatic sums. Okay, and this contains, and union n in contains all sufficiently large natural numbers. And if we prove this, what I have written down here, that proves our theorem. Okay. This will prove the desired bound because this S here, this is of the same order of the magnitude, and so this will prove our desired bound. So what we have to show is that this S into Sn, what is the Sn? The Sn is these things, the subset of squares Bn with the same lying the same partition, and whose cardinality we know is square root n by ck log k, and we also know that it does not have any small prime divisors. Then if we can show that this S into Sn contains intervals, then reasonably large intervals, then we will be able to show that this is the case. Okay, so now this problem was reduces the problem of finding the monochromatic sum, this obtaining a bound for this S to obtaining a to showing this S into Sn contains an interval of reasonably large length. Okay, now I will tell you, explain you a result of Sarkozy and Lev, which will reduce the further to the problem that you don't have to tell me that S into Sn contains an interval, but S into Sn, if it is some dense subset of an interval, that is enough. So here the problem was reduced to showing that certain S-fold sum of the Sn contains an interval. A result of Sarkozy and Lev will reduce the problem to showing that this S into Sn is a certain dense subset of the interval. Okay, so from the interval you go to the dense set. All right. So okay. So how is that the case? Okay. So what is this is a result of Sarkozy form which was mentioned by Lev. And by the way, this is a theorem which I first encountered when I was working with Professor Desue on zero Fourier subsets of Z mod PZ. Okay. It's the result says the following, that let A is a subset of 1 to L with cardinality of A is greater than equal to L by K plus 1 plus 2 plus for some K belongs to N. Then there exists a D. So then 2K plus 1A contains multiples of D. So it contains an arithmetic progression of the length L, but not only that, the common difference you have an upper bound, and which is less than equal to roughly the density of the set. The common difference is bounded by the density, and this 2K plus 1 A contains this multiples of D. Okay. So now let me draw certain corollary from using this result, which is due to Hegivari and Heneka, which they used in their paper, and which will transform the problem, as I mentioned, the problem of showing dense set, the intervals to the dense set. So what is the thing? So now even if you don't, one does not know the initial problem, this question is very elementary and one can understand it. And it is pretty useful in many situations. As I mentioned, at least in 2 of our papers we have used, one in an article with Jamak and one in this paper. So what does it say? So it says that suppose you have A is contained in M to 4M. Okay. So how many integers are there? Roughly 3m. And this is roughly, you should forget this 2, and these are just technicalities. The 3m by some k plus 1. Then, and suppose further that there exists x naught in A, which has no smaller prime divisors. How many small means 2k plus 1. Okay. Then for all sufficiently large n belongs to SA, and the S can be bounded with the density plus this ratio of n by m. Okay. Of course, if this is contained in m to 4m, if I want some very large natural numbers, then I cannot write it as a sum of few summits. But if the n is if the n is small, not particularly large in terms of m, then this thing that this ratio is bounded, and then this S is not too large. Okay, so how do you prove this? So you define B is equal to A minus M. Then B is contained in 1 to 3m. So it is also contained in 1 to 6m. Okay. Okay. See, why I am considering this? Because you see, when you consider the problem, the result of this Sarkozian layer, then it gives you an arithmetic progression of length L. What I am saying is that if you want the arithmetic progression of length 2L or 4L, it is not particularly difficult because you have to just take little more summits. So, okay. And we have the cardinality of B is equal to cardinality of A is greater than equal to 6m by 2k plus 2 plus 2, because I am just multiplying whatever has been given, this first term in 2 and in the numerator, 2 in the denominator. Okay. So therefore, the result of Sarkozy will tell me that there exists a common difference G less than equal to 2k plus 1, such that this 4k plus 3, this B, contains an arithmetic progression of length 6m. Means this multiples of D with the length 6m. Okay. Now choose x naught such that x naught has no small prime factors, and that is there by your assumption. Then such an x naught will be co-prime to this D, because D is less than equal to 2k plus. So that means D belongs to Z mod x naught Z star. Now x naught is less than equal to 3m. So this you are taking a D and then taking the multiples of how many? 6m multiples, consecutive multiples of D. That means that this multiples will cover all the residue classes modulo x naught. Because you are taking all the multiples of D is your coprime, and you are taking the consecutive multiples with the and also the okay. So therefore, this hence D, this thing will runs over all the residue classes modulo x naught. So given any n belongs to Z, that means that there exists R belongs to Z and B belongs to 4k plus 3b, such that n is equal to B plus Rx naught. That is the meaning. I am just rewriting that this covers all the residue classes modulo I. Okay, so 4k. So now we can take this B to be belongs to 4k plus 3a, because if you consider this translate also, that will also cover all the residue classes. So then if n is greater than, but generally this R may be negative. Okay, but so how do we ensure that this R is not negative? By taking this n to be bigger than equal to B. But B, I don't know where does it, which element I need to take. That will depend upon the choice of n. But anyway, I know that this B belongs to this 4k plus 3a, and this 4k plus 3a is contained in this interval. Okay. So if I take n to be greater than equal to the maximum of this interval, I am assured that this R is positive. So therefore, then if R is positive and A belongs to 4k plus 3a such that n is equal to A plus R x naught. And okay, and so, and moreover, we can, from these things, we can get a bound because R is positive and less than equal to n minus A by x naught, which is less than equal to n by A. So A you have belongs to 4k plus 3, and this R x naught, R is n by m. So therefore, this n belongs to 4k plus 3 plus n by m S A. All right. So in fact, we will show now that Sn, which was this contained in n to 4n, so 6n, Sn will be contained in 6n to 24n, and we will show that the 6Sn is greater than equal to n by A naught, with A naught less than this. And using the result of earlier thing what I mentioned, that will solve the problem. Okay. Because then what did we do? Let us, even if you have forgotten the details of the proof of this corollary, what was it? That if you have a cardinal T of A is greater than equal to the length of the interval divided by the density, then how many summands you have to take as some constant multiple of that density, essentially. Because if n is not too large, n is less than kn, then this S which you have to take is less than the density. Okay. So therefore, so if we show that the 6Sn is greater than n by A prime, then if I take this A prime into some constant multiple of A prime into 6Sn, then that will contain interval. Because Sn, remember, also does not has an elements which do not have a small prime divisors. So okay, so now let us. So now the showing that this lower bound for the 6Sn is via very useful things, and this is very much in additive combinatorics and analytic number theory. This function additive energy is very much used and very useful, and which will give you a lower bound of this 6Sn. So now let me define what is an additive energy and give you a lower bound for this 6Sn in terms of the additive energy for these things. That is just a basic Cauchy-Schwarz inequality. So what is also, let Z be an abelian group and a subset of Z be a finite subset. So in our situation, Z is just the set of integers, which is an abelian group. And A is then A will be just Sn, which is a finite set. The set of squares were infinite, but we have restricted ourselves to Sn, which is the set of squares lying in between n to 4n, satisfying certain conditions and a certain subset of that. So that is a finite set. So the nth additive energy of A is the number of solutions of this equation. That the A1 plus An is equal to An plus 1 plus A2 with all AIs belonging to A. So okay, so now let me we will rewrite this thing in slightly different manner. So let me define this RANX is equal to number of n tuples in A such that their sum is X. Okay. Then you can see that this is just not additive energy is nothing but RANX square. You see this the total number of solutions for this equations you can partition according to the what is the left hand side sum. So that will be a disjoint partition. And for each partition, this if I fix what is this sum, then the number of such tuples is RAN square. Okay, so therefore the E and A will be equal to summation RAN X square. So NA we are writing as A1 plus AN, AI's belong to A, denote the n-fold subset. Then RAN X is greater than 0 if and only if X belongs to NA. Okay, and summation of X belongs to NA, RAN X is nothing but cardinality of A to the power n, because here you are counting all the tuples with multiplicity according to the sum. So now by Cauchy-Schwarz inequality, this is less than equal to this left hand side square is less than equal to this. Now this is nothing but the additive energy, and what is this? This is nothing but the cardinality of NA. So therefore what you get is that cardinality of NA is greater than equal to this. If I can take this E and A on the left hand side, then that shows that if I have an upper bound for this E and A, I can obtain a lower bound for the n-fold sum set. So therefore, so we had earlier reduced the problem of showing that 6Sn is a dense subset of n 6n to 4n, 24n. Now the problem is reduced to obtaining an upper bound for E6Sn. So what is the theorem? So what is the statement? So if I take the A and L to be sufficiently large, then for all sufficiently large integers n depending only on A and L, and any subset S of the squares in the interval n to 4n. Yeah, so this is anyway, with this is contained. A is the set of the squares intersection n to 4n, satisfying the following assumptions. What are the assumptions? First, that the set of squares in this interval, total squares square root n. So that should be the set of the squares should not be too few, that there should be square root n by A. Many. Moreover, for all S belongs to S, this S product P less than equal to A to the power L, P is 1. Okay. So we will in our things we can take L is equal to 12. So so now this coprimality condition which we earlier used was used or have been already used in a result in the application of Sarkozy and Leib, but it will be also used here in a very essential manner, as we will see. Then E6S is less than equal to this bound. Okay. And if you follow the whatever I earlier said, then this is what will apply the result. So first thing is that, as I mentioned, that this particular condition is essential. Means that if I remove this condition, the result is no longer true. Which means that I have to give you an example of a set which satisfies the other this first property, but not this bound on E6S. So anyway, this is so okay. So therefore, That is what I said, that if I obtain this result, then I will get a result. Okay. So the condition that is essential, because if you remove this condition, the bound on additive energy is no longer holds. So what is the example? So suppose instead we have this S is equal to A square, N square, and N is lying between M and 2M. So you take all the squares in this interval which are multiple of A square. How many such squares are there? There are M many squares, because the number of possibilities for N is M. So therefore, and each possibility will give you a different squares. So the total number of the cardinality of the set is cardinality of M. And we can see actually this E6S is essentially constant times M to the power 10. That essentially follows from what Professor Desue was doing, because you see here the squares are, you are taking essentially all the squares between M and 2M. Okay. And so therefore the additive energy will be, you can remove this A square, and the additive energy will be the additive energy for the set of squares lying in this interval. Okay. And then R6 of the number will be, if N is not close to 6M, then it will be essentially whether if there is no lower bound for this. So, and for R6N, we know the asymptotic. So therefore, the summation R6N square, we know the asymptotic. Yeah? So therefore, that will give you, is that not correct? So therefore, that will give you a lower bound for the E6S of the order M to the power 10. And then when you put in that if this also holds, this E6S is less than equal to this bound, then what you get up, see on the one hand this is less than, and on the other hand it is of the, so then what we will get is essentially, because there is a lower bound, upper bound if you assume, and there is a lower bound which we have proved. So that will essentially tells you that this square root n by a is greater than square root n into this, which means that 1 by a is greater than this function, which for the a sufficiently large is not true, as you can verify. So therefore, for this particular set, this upper bound for the additive energy cannot hold. Weaker upper bound. This is essentially as close to the maximum you can, right? I am not sure. I'm not sure. I think I'm not sure. Here in this particular case, it is as close to the maximum as you can get, right? So for any alpha belongs to 0, 1, let S alpha is equal to this thing. Now this you have seen many times this orthogonality relations by now, and this then if you use the orthogonality relations, then this E6S can be also written in terms of this S alpha. It is exactly equal to S alpha to the power 12 D alpha. Okay. But on the other hand, this way of writing down this E6S is not particularly useful, for the reason that now you don't have the full set of squares and only a dense subset of squares. Now, for an instance, when you obtain and you estimate these things on the minor arc, one thing which you use is while differencing and some sort of Parseval or Huas, whatever, but nevertheless, while differencing. While differencing does what? That it here this S is a S square because this is in the subset of the squares. If it is a full set of squares, it will convert it into the geometric progression. But if you have only a dense subset of squares, then it will, when you apply while differencing, you will get a geometric progression, but an incomplete geometric progression, which we don't know how to sum it. Okay, so therefore this is not very useful way of writing down. Okay, so because as I say that we only have a certain dense, so when, if you apply while differencing, we will need to evaluate certain incomplete geometric progressions which we don't know how to sum. Okay, so therefore we need to replace it. For this reason, what we would like to do is that E6S is less than equal to some 0 to 1 S alpha to the power 11 F alpha, where F alpha will be a weighted sum over the set of entire squares. Okay, why weighted sums of the squares we will see. Because you see this, I will like to utilize, we would like to complete the set of squares, but we would also like to use the fact that the squares are, yeah. Sure, sure, right. Sorry, yeah. Yeah, I think in the next slide, I would have probably corrected it. Okay. Yeah, as Olivier correctly mentioned, it will be S alpha to the power 6 and S minus alpha to the power 5 into F alpha. Okay. So in any case, so for all, in this things, all the sums were summing over this is dense subset of squares. In these things, 11 of them will be summing over the set of your given set, and one particular sum will be varying over the entire set of squares. Okay, not exactly entire set of squares, but the set of squares in n to 4m which are co-prime to all primes less than e to the l. This is not very serious thing. This you can handle because you can divide it, partition it according to the residue classes, modulo a to the power l. Okay. So now this is a strategy which has a, it's a, so how do we estimate this E6S? This is due to Ramare, Ruza, then developed in Suri and Ramare, and then. So what we'll do is that U is equal to product P less than equal to a to the power L, P. Then what we will show is the first this inequality that E6S is less than equal to. So now for the estimating this E6S, our first, there will be few steps, and our first step is this. Okay. So phi tau u by 2 root n, x belongs to SS, this one is an invertible square modulo 4u. Okay. And here tau u is the number of divisors. So let W is equal to a to the power L, U is equal to these things, and capital W is 2u. Why do I take capital W is equal to 2u? You will see when we encounter certain Gauss sums, and this Gauss sums will vanish by taking this choice of W is equal to 2u. So here you see in this W, I have taken almost the product of the primes less than equal to WP, except the 2 I have taken with multiplicity 2. And that will be important when we encounter, because the certain Gauss sums will vanish because when we take this W is equal to 2u. And that is one of the vital thing in the proof of this. So then define the function alpha from R to R, these things, T and beta this function. Then this function is basically when the set of squares are between n to 4n, this function beta t will be taking the value at least 2 by 5. Okay, so for now the inequality which will play a role is that this inequality, that 4 by 5 times square root n isn indicator, this is an indicator function of Sn, is less than equal to 2n beta n square indicator function of n and w is equal to 1, which I can rewrite it as a summation 0 less than equal to r less than w, r and w co-prime, and n congruent to r mod w 2n beta n square. Okay. So as I was mentioning earlier, that one of the variables we will fix means value over all the integer squares and not just the dense subset of squares comes via this inequality. But then how does this relate to E6S? Now, if you now E6S is the sum of this N1 and sorry this right. So maybe I can rewrite here. So E6S is, can one see this? Is equal to summation N1, N6, N1 prime belongs to S, and N6 and indicator function of S N6 prime and 6 prime, such that N1 plus N6 is equal to N1 prime plus N6 prime. Okay, I could remove this and then write down that indicator of Nx prime also belongs to S, but I don't want to do that because I want to utilize this inequality. Okay, now the point is that these are all non-negative functions. So if I have an upper bound for this indicator function of S nx in terms of some other function, I can replace it some another function fn prime, not prime, and then replace it by this. So if indicator function of Sn is less than equal to some other function fn, then I will get this bound inequality because these are all sum of non-negative functions. Okay, and that is what we use here because indicator function of S is less than equal to 2n beta n square by square. Actually, this is essentially square root n. Okay, and this. So after this, we will forget that we are keeping on working with only the squares between n to 24n. But here is where we will use the fact, because in beta does not essentially takes care. Okay, it does, but okay, because the support of beta. This is where we will use the fact that we are not working with the full set of squares, but only the squares which each of them being large. And that will give us a saving of square root n, which is important for us. Okay, so we get this inequality. Now, in writing this way, this looks complicated, but actually when you write it in the integral, this becomes simplified slightly. It becomes as, okay, S bar is here, fine. So S alpha to the power 6, S alpha bar to the power 5, and phi minus alpha, where phi is this function. So now on the major arc as well as minor arc, what will play a role is the understanding of this function. Okay, which is essentially over the complete set of squares, not an dense subset of squares. So therefore, we have a better chance of understanding it than if we are working with some arbitrary subset of squares. Okay. Because you see now no longer this function is non-negative. Okay, earlier we started with non-negative functions, so we could bound it by the completing. But if you have oscillating sums, you cannot bound the sum by a complete sum. Okay, so now in the earlier one, this goal was this square root n. There was a square root n in the main term and the square root n in the second term as well. But because we have got a saving of this square root n from here, so what actually we need to prove is that multiplied with the square root n. So the integral this here needs to be proved, this 2 tau u, this one plus O of s to the power 11 by a. Because one extra square root n was the saved from the bound on the indicator function of s. So now I have to define what are the my major arcs, what are my minor arcs. So I have already defined this W. Let us see, here it was W. W was a product of P less than equal to A to the power L. W is equal to 2U. Okay, so the W here is bounded from function of A. Okay. And Q I will take W square A to the power 12. So here again, in the capital Q is bounded for me. But the length of the interval I will take L is equal to log n square and M is equal to N by L. Okay, so the length of the interval is N by log n square. And then my for the any major arc will be for A by Q when Q is less than equal to Q, this capital Q, which is some function of A, bounded function of A. Okay. Then this is the length of the interval is A by Q to A, the centered around with the distance 1 by M. Okay, so log n is square by n. So this is quite a small interval. Although A by Q is bounded in the bounded range. Okay. And then minor arc will be just the complement of the major arc. So for the estimates of the minor arc, what we will show is that this is less than cardinality s to the power 11 by a. So therefore, if you remember that we needed to bound this in terms of the two things. One was this tau u into some x1 blah 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 minus this thing's invertible. So that was the first term, and the second term was O s to the power 11 by a. So then this will tell me that the minor arcs, the contribution from the minor arc is going into the error. So okay, so this follows from I will not go to the details, but this is because this is a complete set of squares essentially. This follows while differencing and Appel's partial summation. If you do, then this supremum is less than n by a to the power 6. You can prove it by using the standard. Okay. So using this bound, this will be this n by a to the power 6. And then now you have taken the modulus inside. So this is a non-negative terms you are integrating over a minor arc. So then you can complete now the full integral. Okay. So this, once you have taken out this the supremum of mod phi alpha, which will be valid only for alpha in the minor arc, when alpha is in the minor arc. After taking it out, you just complete the integral. And then this thing can be estimated using Parseval and R5, the number of ways n can be written as a sum of 5 squares. Professor Disway gave you an asymptotic formula for R5n because in the variance problem. So therefore, now this okay. So therefore, therefore you can obtain a bound for this, which will be n to the power 3 by 2, and this is nothing but counting all the elements in n belongs to s to the 5 with multiplicity. So that will be s to cardinality of s to the power 5. Okay, so therefore this will give us that E5s is less than n to the power 3 by 2 s to the 5. And if you do this, then basically you will get this what we were claiming, that this minor arc contribution is s to the power 11 by a. So therefore the minor arc is taken here. So yeah, so we use the orthogonality relation to relate E6s to this Fourier integral. We decompose into the major arc and minor arc. On the minor arc, we produce, which is acceptably small because that is going into the error. And then the major arc will contribute the main term involving tau u and the condition of on fx being invertible square modulo 4u. Fx was this x1 plus x6 minus x7 minus x8 minus x9 minus x10 minus x11 is invertible square modulo 4. So now we need to understand the contributions coming from the major arc. So again, as I mentioned, that what we have one positive thing about us is that this particular things, we don't know how to understand this S alphas. We can understand this phi alpha because that is over the complete squares. Okay. So then, and which can be actually obtained by using Euler-Maclaurin summation. Okay, so therefore, this if we define, I will just write down the final answer. GRA by Q is equal to this Gauss sums. So then Euler-Maclaurin summation will tell me that this phi alpha is equal to just this first term you concentrate on, and this error is negligible. Okay. Of course, when you're working, you have to see that this is really negligible, but those are the details. I will not go into this things that why this negligible. As I have written down in the slides, but I am not going to explain now in the lecture. Now comes the really an interesting part, that this is a priori. Yeah, a priori, this is this GRAQ is varying over all the Q less than equal to capital Q. Okay, but now we will see that actually this is essentially not varying only for Q dividing 2W. When Q does not divide 2W, either this sum is 0 or too small. When Q is not dividing 2W, and W is, remember, is a small product of the small primes. So it's really small. So therefore, this is either this GRA function is either vanishing or it is too small. So that is essentially given by this lemma, which is based on actually, as Suri tells me, that it's based on the work of Tim Browning and Prendeville, where he got notice this. And then this GRAQ is equal to 0 unless Q divides 2W or there is a prime P greater than W such that P divides Q. Okay. So then this 1 by Q mod GRAQ is less than equal to 2 by square root 2 by W when Q does not divide to 2 times W, capital W. And W is, remember, is a product of P less than equal to a to the power L. So it is not a small number because we need only a saving of certain powers of A in the below. Okay. So what is the key identity? So now remember what was this GAQ? This is a sum of certain polynomials, namely which polynomials over Q. Certain exponential sum, this polynomial over Q. So now the point is that if Px is equal to this polynomials A into R plus W square, and you define this D is equal to Q, with D1 is equal to Q by Q square and D2 is equal to this, then you can write down this sum as the product of these two sums, namely 0 less than equal to M1 less than D1 I will prove this in the next slide, into 0 less than equal to M2 less than D2. Okay? Before I give a proof of this, let us see what are the consequences of this. This means that this left-hand side vanishes if this particular thing vanishes. And this particular thing vanishes unless D2 divides C1. Because this is a sum over all the D2s of exponential C1 M2 by D1. Okay, so unless M2 divides C2, this will vanish. D2 divides C1, this will go away. C1 is this term, 2WAR. Okay, sorry, the coefficient of the X term. Okay. So now so now you for this is proved by this M1 M2 to M1 plus M2 D1. This is a bijection from 0 D1 cross 0 D2 to 0 D. Okay, for showing this, because now first showing bijection, I have to prove two things. One thing is that this is mapped inside this. This map maps to 0 D1, 0 D2 inside this, but that is easy to show. And then once you know that, then to verify that this is a bijection, since the domain and the range have the same number of elements, D is equal to here D1 into D2. Okay, then, sorry, I did not write. Yeah, D is equal to D1 into D2. Then, so domain and the range have the same cardinality. So therefore, if I know that it is injective, then it is bijective. Okay, and that is because if they are same, then M1 minus M1 prime will be congruent to 0 mod D1, and then M1 is lying in the interval 0 D1. That means M1 is equal to M1 prime, which will show that this is also. Okay. And then you can see that PM by D. Why I care about PM by D? Because here there is a PM by D. Okay. And so therefore the PM by D is same as PM1 by D1 and C1 M2 by D2 modulo Z. Okay. And for this particular sum, E to PM by D, you only care about what is PM by D modulo Z. Okay. So therefore, the sum is can be written as a product of two sums. Okay. So therefore, that from there you get the result. Okay. So let me just rush through it. Okay. So then there is a contributions on the major arc. You can write it, and then when you do this, that as I say, that is phi functions. The sum is surviving only for Q dividing 2W, and the rest goes to the error. Now, to exactly estimating those errors is little, I mean, it's tedious, but on the other hand, there is nothing complicated in it. So then you can reduce this TW. So then what you will see is that the integral over the major arc is essentially equal to this integral, if you do all that. Okay. So yeah, so then, okay. So this T is equal to TW, and you can rewrite actually this TW. One can notice that this is exactly equal to what you were trying to prove. This is TW is exactly what is you are trying to prove that. Okay, so the evaluation on the major arc is exactly equal to this plus O of S to the power 11 by E, which will again go into the error term. So we get the result once you notice this. So the contributions on the minor arc was essentially Weil differencing and a Bell's partial summation, and contribution on the major arc was essentially Euler-Maclaurin, which is a standard thing to complete into the Gauss sums, and the Gauss sums vanishes, satisfy certain nice properties. So therefore, if you observe all those things, then basically what you get is this E6S is less than equal to this. Okay, so now I have to estimate this quantity. Okay, the trivial bound is s to the power 11. Okay, and what we want to prove is the s to the power 11 by square root n into some function, which is a small function, except that in the front of this we have this tau of u, which is spoiling the game. Okay, so somehow we need to bound this x to the power s11 in a better manner so that we can get rid of this tau of u. How much time do I have? 10 minutes. Okay. So what we will prove is that this is less than s to the power 11 by tau u into exponential this 3 log 2 blah blah blah, and that is what will then tau u and tau u cancels, and that is what will give us the result. Okay, so how do I show this x belongs to S11, fx is invertible, this thing is this, less than this particular quantity. So now we define this, let z be the subset of integers, c is equal to ci, we have finite sequence of integers, and ru zc as the set of triples x, y, I belongs to z cross I such that x square plus y square plus ci reduces to an invertible square modulo u. Remember your fx was, so what are we trying to estimate is this x belongs to S11 such that x1 plus x2 plus x6 minus x7 minus x8 minus x9 minus x10 minus x11 is belongs to z mod uz star square. That is what we are trying to estimate. So I can fix all but first two variables and write down in terms of this. Okay, so now this one, if I fix, then this will be certain sequence Ci. Okay, and we are trying to estimate. So therefore, this x square plus y square plus, so here z will be our s only. Okay, and the Ci's will be this sequence for, so the indexing set will be s to the power 9. So take z is equal to s and I is equal to s to the n, with Ci is equal to x3 plus these things. So here it should be x3, okay, in belongs to S9. Then x belongs to these things, RUSC is a bound. So for I belongs to I, if I define alpha I AB is equal to 1, if A square plus B square plus Ci is invertible, square in Z mod UZ and 0 otherwise, then and let A be the number of Z belongs to Z, such that Z is congruent to A modulo U. Okay, then I can rewrite this RUZC is equal to summation over this indexing set AB belongs to Z tilde square alpha I AB MA into MP. And this MA and MB satisfy these bounds. So now I can define this RUZC is a particular, so we will define a bilinear form on Rn cross Rn for certain suitable n, such that this RUZC is the evaluation of that bilinear form on certain spatial lattice points inside a certain convex set. Okay? So RUZC will be an evaluation of this, some bilinear form can be viewed as a value of a bilinear form inside certain convex subset, inside on a lattice points. So we are trying to estimate this RUZC. So let us see what is the bilinear form. So bilinear form is this, that summation AB belongs to Z mod UZ star square alpha I AB XA YB. Okay. Then all this MA MB will satisfy this condition. So now this defines me a convex subset. So that means that MA MB belongs to this convex subset defined in this X belongs to R to the phi U summation this thing. So this is a convex subset. Okay, and this is because this bounds. So that shows that this is a compact convex subset. Now, Klein-Millman theorem says that if you have a given any compact convex subset, any element inside the convex set is can be written in terms of the convex combinations of the extreme points. Okay, so this RUZC, which was the some evaluation of this alpha, this bilinear form inside some lattice inside this convex subset, is less than equal to the maximum of this bilinear forms attained inside this convex set. And the maximum of bilinear forms inside a convex subset will be then, using Klein-Millman theorem, will be achieved at the extreme points. Now, what is the advantage? Because as Balasubramanian was saying that you have extended the subset in the morning, so therefore this bound may be a little too big, probably. But on the other hand, the advantage is the extreme points might have a nice structure. So you will have a better chance of obtaining an upper bound for this over this extreme points. It will be easier to obtain an upper bound for this bilinear forms over the extreme points. So therefore, this follows from the Klein-Millman theorem that fxy is less than equal to fx star y star where there are extreme points. 5 minutes ago. That if x star is an okay, so yeah, so then okay, so then you can obtain these things. Okay, so okay, so then you can okay, so then you can. Then I have to go to this local problem, but which is using this holders and Hofding's inequality, but I don't think that I have time. Okay, I'll stop it.
Thank you very much. Are there questions? You know that you are still a few minutes if you want to add. I didn't want to tell you something.
Anything interesting will take more time and then.
Fine. So thank you very much for this nice talk. Are there, yes?
Yeah. The arguments are same, so therefore it is not particularly.
Good. We thank the lecturer for the lecture and having taken time to come here and interact with us. Let me again give a great applause. Thank you.